Well, welcome to the Explainer. Today, we're taking a deep, component-by-component dive into the architecture of a modern, highly scalable URL shortener. We use these things every single day. You click a tiny link and magically, instantly, you're looking at a full web page. But the system making that happen? Well, it's actually anything but simple.
So, what does it actually take to build one of these from scratch? If we put on our lead architect hats for a minute, what is really happening under the hood when you click that short link? How on earth does the system handle millions of clicks without crashing, process all that analytics data, and do it all without making the user wait? That's exactly the puzzle we're going to solve today. Here's our roadmap for this explainer. First, the big picture architecture. Second, creating the short link. Third, the high-speed hot path for redirects. Fourth, asynchronous click analytics. And finally, the orchestration and infrastructure pulling it all together. All right, let's jump right into section 1, the big picture architecture.
What's really fascinating here is how the traditional monolithic approach is totally broken down into a highly specialized 3-microservice architecture. Notice how different tools are specifically chosen for different jobs. First up, we've got the URL API built with Django and the Django REST framework. This handles your standard CRUD operations, creating, reading, and deleting those shortened URLs. Then there's the redirect service built with FastAPI. This is the performance-critical engine for the whole system, and it is designed purely for speed. Third is the analytics service, also built in Django, which is completely decoupled from the main API, so it can process click events and aggregate stats in the background. And tying the whole shebang together is our front end, a sleek, single-page application built with React, Vite, and Tailwind CSS. Let's move on to section 2 and see how this actually works in practice, starting with the very first step, creating the short link. Picture this. Your React front end starts sending requests to the Django API, but right out of the gate, we hit a massive security challenge. How do we stop abusers from just spamming the system? I mean, if someone writes a script to generate 1 million links a minute, they'd easily overwhelm our PostgreSQL database. The incredibly elegant defense mechanism here is a token bucket rate limiter, and it's powered by Redis. When a request comes in, the system checks the user's API key or IP address. It uses this super fast Redis command called anchor to atomically increment a counter for that specific user. If it's their very first request, Redis assigns an expire time, a time to live, of 60 seconds. If that user's counter hits over 100 requests within that minute, bam, the system instantly blocks them with a 429 too many requests error. And the absolute best part? The TTL automatically resets the window when time is up. No complex database cleanup required at all. Okay, so once we're safely past the rate limiter, we actually need to generate the short link. 56.8 billion. Yeah, billion with a B. That is the massive scale of unique URLs the system can support, using just a tiny 6-character base 62 string. So how do we get this string? Well, we definitely don't guess randomly. The Django API simply inserts a new row into the PostgreSQL database, and Postgres hands back a unique auto-incrementing numeric ID. We take that pristine ID, run it through a base 62 encoder, which uses numbers, lowercase letters, and uppercase letters, and we're done. It's completely URL safe, it avoids collisions entirely, and it's incredibly compact. Let's quickly recap the exact chronological sequence the Django API takes to safely generate your link. Step 1, it validates the user's input, making sure it's an actual, correctly formatted URL. Step 2, it checks that Redis rate limit to make sure the user isn't a spammer. Step 3, it creates a placeholder database row to grab that auto-incrementing ID. And step 4, it generates the base 62 code from that ID and updates the row. Just like that, in mere milliseconds, your short link is born. Which brings us to section 3, the high-speed hot path. This right here is the most critical part of the entire system. It is the absolute express lane. So when a user clicks a short link, they hit our FastAPI redirect service. FastAPI was chosen specifically for its killer async performance. But here's the thing. Even the fastest framework in the world is going to be bottlenecked by database speed. That's why caching is literally a make or break feature here. We have to look at 2 scenarios, a cache hit versus a cache miss. A cache hit? That means FastAPI checks Redis, finds the original URL instantly in memory, and redirects the user. 0 database load. Lightning fast. But what if it's a cache miss? Well, FastAPI has to do a fallback query directly to PostgreSQL. Once it finds the URL, it immediately updates the Redis cache with a 1-hour time to live. That way, the next person who clicks that link gets the express lane. So the flow is simple. Step 1, Redis check. Step 2, Postgres fallback if we need it. Step 3, cache the result. But hold on, look at step 4,
publish event. We need to track analytics for this click, right? We want to know where the user came from and what device they're on. But if we try to do a database write right then and there during the redirect, we're going to slow the user down. So how do we get around that?
And that is the perfect segue into Section 4, Asynchronous Click Analytics. Let's look at how we capture all that deep data without ruining the user experience. This is where system design gets really, really fun. If we used a synchronous database lookup, the user's browser would literally hang there, loading while our server wrote their IP and browser data into a database. Unacceptable. Instead, we use an asynchronous RabbitMQ publish. I want you to think of RabbitMQ like a post office Dropbox. FastAPI drops a tiny JSON message into the box with the click data and then immediately redirects the user. It's a complete fire and forget mechanism. The user is on their way, totally unblocked, while the heavy analytics processing happens in the background. If RabbitMQ temporarily goes down, sure, we might lose an analytics event, but the user's redirect still works flawlessly. It's a brilliant architectural trade-off.
Meanwhile, working hard behind the scenes, there's a separate Django analytics consumer listening to that RabbitMQ queue. When it picks up a message, it gets right to work. First, it parses the user agent to see if the click came from a mobile phone, tablet, or desktop. Second, it takes the user's IP address and hashes it using SHA256. This is absolutely crucial for privacy compliance. We can track unique visitors by looking for matching hashes, but we never actually store the raw IP address. Next, it extracts the referred domain, like Twitter or YouTube, so we know where the traffic originated. Finally, it stores all this into a dedicated analytics database as a raw click event.
Let's focus on the number 10 for a second. This is our RabbitMQ prefetch count, and honestly, it's a super clever configuration. By setting this prefetch count to exactly 10, we prevent one slow analytics consumer from hoarding thousands of unacknowledged messages in its memory. It forces the system to distribute the load fairly, processing exactly 10 messages at a time. This keeps our memory footprint lean and makes sure our background workers are running at peak efficiency. But we still have one more analytics problem to solve. If our React dashboard tries to load stats for a link that has, say, 1 million clicks, querying all those raw click events on the fly would take forever. To fix this, the architect added a periodic aggregation job. Basically, a command called aggregate daily runs in the background. It takes all those millions of raw events and rolls them up into a clean, daily stats table. So when you open your dashboard, the front end simply queries this pre-aggregated table, instantly serving you those beautiful charts like the exact percentage split between mobile and desktop users without bogging down the database with incredibly expensive queries.
Finally, let's wrap things up with Section 5, Orchestration and Infrastructure. How do we actually run all these separate moving parts?
The entire distributed system is glued together using Docker Compose. Our Docker Compose.yaml file is basically the ultimate blueprint for the whole operation. It defines our front end, served up via an Nginx reverse proxy, our blazing fast caching layer using Redis 7 on Alpine Linux, and our message broker with RabbitMQ. But most importantly, it defines our databases. And notice, we don't just have one massive database. We've got URLsDB running on Postgres 15 for the core URL API, and a completely separate AnalyticsDB instance just for our click events. This physical separation gets to the absolute golden rule of this architecture. Each service owns its data, and they cannot accidentally couple through shared tables. By physically separating the URL database from the analytics database, the architect is ensuring true microservice resilience. Think about it. If the analytics database crashes because of a sudden, massive influx of data, your URL API, it just keeps running. People can still create links, and most importantly, the hot path can still redirect users. They are functionally isolated.
Which brings us to a final, slightly provocative thought to leave you with today. When you look at an architecture like this, using Django for robust CRUD operations, FastAPI for high-speed async redirects, Redis for caching and rate limiting, and RabbitMQ for fire-and-forget event pipeline, you really have to ask yourself about your own projects. Are you picking the right tool for the job, or just the one you know? Because this architecture proves for sure that separating concerns and blending the right technologies creates a system that is incredibly fast, deeply resilient, and built to handle massive scale.